Good morning, geometry class. I'm going to give you guys a brief video in which I describe the new theorem from section 12-5 and how it's applied, and also go through a few examples for you. So section 12-5 is basically about similar solids. So in the past we've dealt with plane figures that are similar, but surprise, surprise, solids can also be similar. And really the way you determine whether two solids are similar is the exact same way that you determine whether two plane figures are similar. So in plane figures, that is two-dimensional figures, you determine that they are similar if they have basically the same shape but different sizes. So basically the way you do that mathematically is look at all the corresponding sides, and all the corresponding sides will have the same ratio. So if I have two figures here, say, I don't know, two quadrilaterals that have something of a boomerang shape, something like that, and say the length of this was 5 and this was 4, let's just do another 5 and 4, and this was 10, 10, 8, and 8. These would be similar solids, assuming that all the angles were the same measure, because 5 divided by 4 is equal to 10 divided by 8. It's 1.2. It's 5/4. Or you could also look at the ratio between the two. So 5 to 10 is the same thing as 4 to 2. You're multiplying by 2 to get from one to the other. So the scale factor of this, if you remember, is going to be basically 5 to 10, or that's the same thing as 1 to 2. We can simplify that. So 1 to 2 scale factor. That's the way similar plane figures work, and similar solids are going to work in the exact same way. So they have the same shape, not necessarily the same size, and so all of their corresponding pieces are going to be in the same proportion. They're going to be in ratio. So some of our shapes that we have, like say a sphere or a cylinder, have circles, and you can assume that all circles are going to be similar to each other because they're the same shape. So any two circles are going to be similar, and any two spheres are going to be similar as well. Then you get different shapes like cylinders. So let's get a cylinder drawn here. Something like that, and you could have a smaller one as well. So I have two cylinders here, and the way you would tell if they are similar would be if they have the same proportions, the same ratios. So you could look at the radius, and you could also look at the height. Those are the two measurements that we have in cylinders. We have the radius and the height. So if the radius here is equal to 14 and the height is equal to 10, and here the height is equal to 5 and the radius equals 7, then they would be similar because 7 times 2 is 14, 5 times 2 is 10, so the scale factor is 1 to 2, or 2 to 1 if we're going from left to right. Doesn't really matter. Okay, so let me just go ahead and give you theorem 12-11 then, because that's where the meat of this section is going to be. So the meat of this section is in theorem 12-11, and this is going to look similar to another theorem that we've had from our last section. So basically, if the scale factor of two similar solids is a to b, then we're going to have three things that follow. So if scale factor of two similar solids is a to b, then, and we have three parts. First part, we'll call it A, is that the ratio of the corresponding perimeters is a to b. Note the word corresponding perimeters. In our other theorem, we could just say perimeter because there's only one perimeter on a plane figure. But in solids, you might have to identify which face's perimeter are we looking at. So let's see. Perimeters is A to B. Part B, the second part of this theorem, talks about the ratio of their base areas, the lateral areas, and their total areas. And I'm just going to abbreviate that by saying any area. So any corresponding piece of area is going to have a certain ratio as well. So the ratio of, I'm just going to say corresponding areas, and that could be lateral area or a base area or total area or even just some random side that you want to look at. So this is going to be a more broad definition than what the book gives. So the ratio of the corresponding areas is, and see if you can guess what it's going to be. Put a line here to divide that. It's going to be a squared to b squared. So far, this is actually pretty much the same theorem that we've had before, where we have two similar figures that are two-dimensional. The ratio of their areas or any length inside that figure is just the scale factor a to b, and the ratio of corresponding areas is going to be a squared to b squared. So far, this is exactly the same as we've seen before, but applied to three-dimensional shapes. Now, part 3 is the new part for this section. Part 3, or C, is that the ratio of the volumes is, and see if you can guess it, there's a pattern, so a to b, a squared to b squared. The ratio of the volumes is going to be a cubed to b cubed. So the ratio of volumes is a cubed, so a to the third power, to b cubed. And just a reminder, in exponents, that means a times a times a, and that's b times b times b. You just multiply by itself that many times. Okay, so that is the theorem here. Let me go ahead and move this sheet over so I can give you a couple examples. So what I'm going to do for examples, I'm actually going to work through the first few classroom exercises of telling whether the solids are similar, and then if they are similar, there's several things that we need to do as well. So classroom exercise on page 510 if you want to follow along, number 1. So basically, actually I'll draw it for you still. I have the drawing right next to me, but I'll just do a quick sketch. So, not very good drawing, but we are given two cylinders. One cylinder has a height of 12 and a radius of 6. The second one has a height of 8 and a radius of 3. So the question is, are these similar? And the way we do that is we check to see if their corresponding sides have the same ratio or not. And so we could take either the corresponding sides within the figure or between figures. So I'll show you both ways. So we could look 6 to 12, so the radius divided by the height would have to be equal in both cases. So the question is, does it equal radius over height over here? And we can see pretty quickly that it doesn't. 6/12 is 1/2, 3/8 is not 1/2. So they are not similar. So we get a big no. You could also do this by checking like the radius to radius and the height to height. So you could look at 6 to 3, check to see if that is equal to 12 to 8. And you're going to find the same thing, that this equals 2 and this does not equal 2. It equals 1.5. So these are not similar. The ratio still doesn't hold. So another no. Okay, I was about to ask if there's any questions, but I guess this is a recording, so I can't. I guess I can, but I'd be foolish. Okay, let's see. Number 2 then in the classroom exercises, we have what looks like slices of cheese, since they colored it orange and yellow. So basically there's a triangle on top for both of these. Then we've got a triangle on the bottom and pieces connecting them. And this is going to be dotted. And same thing over here. That's dotted. Okay, and we are given lengths of 9, 12, 15, 12, 8, 6, 10, 8. Alright, sorry that took a little while. But the question is, are these similar? And this is going to take something of a you're going to have to develop a wisdom for how many things you have to check to be sure that it is similar. So by default, you should probably just think, oh, you can check every single side to see if they would be similar. So in this case, it's going to be easier to like compare 9 to 6 and 12 to 8, 15 to 10, and so forth. So let's just set up a bunch of ratios and set them equal to each other and see if we get a true statement. So the top left side, 9 over 6, we're going to see if that is equal to the top right side, 12 over 8. And we can check as we go. So 9 over 6 ends up being 1.5, 1.5. Same with 12 over 8. So we get a check here, little smiley face. We have to check to see if that's equal to then 15 over 10. And sure enough it is. It ends up being 1.5, so another smiley face. And then we need to check to see if 12 over 8 also equals that, and we already actually saw that earlier. So 12 over 8, in fact, is equal to 12 over 8. And so all of these sides are in proportion. Therefore, these two solids are similar. So then the theorem that we just learned, theorem 12-11, would apply. So I think that's what number 3 in the classroom exercise is asking, because it tells you that it is similar. So you need to find the ratio of their lateral areas, their total areas, and their volumes. So let's take a look at that then. So first things first, in order to use this theorem, we need to find the scale factor. So to find the scale factor, we can take any two corresponding pieces and find the ratio. So in this case, I'm just going to do 12 and 8. So the scale factor is going to be 12 to 8, or we could say 3 to 2 is what that would reduce to. And that is going from the bigger one to the smaller one. It's 3 to 2. So the bigger one is 3, smaller one is 2, relatively. Okay, so that's our scale factor. Now we need to find the ratio of their lateral areas. So the ratio of their lateral areas, if you remember, is going to be the scale factor squared. And the reason for that is when you find an area, you get square units. So whatever ratio you have between the two sides, that ratio is going to get multiplied in twice if you ever do a formula for area. So let's see, part A, the ratio of areas. I think actually it asked for the lateral areas first, is going to be the scale factor squared, so that's 3 squared to 2 squared, which is equal to 9 to 4. In part B, actually we don't even need the figure anymore, it asks for the ratio of their total areas, and the ratio of their total areas and the lateral areas is the same. Any piece of area is going to have the same ratio. So it's also going to be 9 to 14 for the total areas. Now part C. That's for the ratio of the volumes. The ratio of the volumes, you can just refer directly to the theorem, is going to be a cubed to b cubed. And you can think about why that is. It's because when you do a formula for volume, you're multiplying like length by width by height. So you have 3 chances to multiply in that scale factor. So the scale factor gets cubed when you go into that. And if you don't quite understand where that comes from, that's okay, as long as you can use the theorem correctly. But you could also like draw cubes and figure out why that works. But I won't do that right now. So anyways, it's going to be the cube of the scale factor. So it's going to be 3 cubed to 2 cubed, which 3 cubed is 29. 3 times 3 times 3. 2 cubed is 8. So we get 29 to 8 is the ratio of their volumes. Now, one thing I want to point out, and this example doesn't really give you that, so that's why I'm pointing it out, is the part A of the theorem, that the ratio of the corresponding perimeters is going to be A to B, so it's the scale factor. And we could prove that with, say, this top triangle here. We could look at the perimeter of this face and find that those perimeters are going to have the scale factor as their scale factor. So the ratio of the two perimeters is going to be one perimeter divided by the other. So 9 plus 15 is 24, plus 12 is 36. Perimeter equals 36. And the ratio here is going, or the perimeter here is going to be 6 plus 8 plus 10, which is 24. And so we could see if 36 to 24 is the same as 3 to 2, and it is, oops, I think I lost my camera here. Let's give that back. Actually, I don't think I need it back, because that's actually the end of the lesson, so very timely. Anyways, so yeah, the ratio of the perimeters is also 3 to 2, the scale factor. I drew that on the sheet, but I don't think you can see it. But anyways, hope you enjoyed this lesson. Hope it's not anything too complicated. It's just an extension of what we've already learned. Let me know if you have any questions, especially if you find that you have questions with like using a scale factor to calculate other values. I think we've had some trouble with that in the past, and I'd be happy to go into that when we meet live. I think tomorrow is when we should be meeting live next. Yeah, so anyways, happy geometrizing.